It's a good transition to Semih, our next speaker here, and Cheriton faculty fellow. So for a quick introduction, Semih is an associate professor in the data systems group, and he does work on both the theory and systems work in the area of data processing and data management. Semih graduated from Stanford and received many awards, including Best Paper Awards at VLDB, SIGMOD, to name a few. And these are the top conferences in his area. So without further ado, Semih.
Thanks everyone for coming. So I'm also going to be talking about graphs, but in a very different context. I'm a core database researcher, so I develop database management systems or components of database management systems. And I'm going to tell you about a project of mine called Kùzu. Kùzu is a modern, new graph database management system that we started building in my group about 4 years ago, but it's taking kind of its own form and own life right now. It's being commercialized at a spinoff that we have here in the Accelerator Center in Waterloo. So it's probably the most serious system that I got to build. And it's in the space of class of database management systems that we call graph database management systems. So my goal in the talk is to tell you about what are graph database management systems and the very brief kind of overview of the vision of Kùzu, why it started, what it aims to do. And then one specific technique that we have integrated into Kùzu called factorization. It's a compression technique, but unlike every compression technique that I've seen in database management systems, which are used at the storage layer, it's a technique that's designed to be used during on-the-fly query processing. So I'll tell you about this and kind of leave you with that. So to introduce you to what are graph database management systems, so I'll just say one very brief sentence about what are graphs and networks. From the perspective of a database management system implementer or researcher, graphs along with tables are one of the two most natural data structures to logically model application data. Okay, they are compared to tables, they're more object-oriented, so you're explicit in your records about which ones are your entities and which ones are your relationships. That's it. That's all that that we need to know about what graphs are from the perspective of essentially a data model. And for people who are not familiar with the history of database management systems, graph database management systems are by no means new. If you looked at the classes of database management systems that have been built in history, starting from 1960s, the very first database management system in history called IDS, to other important classes of systems built like IMS, which was a class of systems called hierarchical systems. Those predate the relational systems. Relational systems come in 70s, but basically every decade there's new classes of systems that are coming up. Object-oriented database management systems, RDF, XML, document stores, property graph database management systems, and we are now in the vector database management system way. So my point is that it's not a coincidence it's not a new thing, this notion of graph database management systems. Across these classes of systems, at least 5 of them can easily be pointed at and said that these are actually database management systems that had adopted a graph-based model as their logical data model, right? So out of all those, this is kind of the latest class of graph database management systems and perhaps the most successful, the most widely adopted. So here's the introduction to this class of systems. Unlike relational modeling, where you structure your records as a set of tuples in tables with clear columns, graph database management systems are very similar. So let's take this example of a financial transaction records. We've got accounts with owners and the countries that they're from, and then there's different types of transactions that might happen between these accounts. So maybe e-transfers, wires, and EFTs. In this simple example, I'm just putting similar types of columns into all of these essentially transactions. In a more realistic one, there could be different ones. In the property graph model, unlike saying that these are all modeled as sets of records in tables, you do separate your nodes, your entities. In this case, the natural nodes would be accounts. But just like your columns, you have key value properties that kind of corresponds to columns. That's how you model data. And the records that represent relationships between entities are modeled as edges between those nodes. Okay, so you got wire edges, e-transfer edges, and maybe EFT edges. So it's very similar to, there's no depth to the data model. Okay, but you're getting a bit more object-orientedness now that you have these notions of objects or nodes. And what this gives you is that, I'll come to this. Let me first actually complete this. The query languages, which is the second important feature of any database management system, they're very similar to SQL. They're meant to be like SQL. This is a snippet from the Cypher query language, the language that originated from this system called Neo4j and that Kùzu adopts. But they're SQL-like, so instead of a select, you have a return, which is where you kind of do your projections. Instead of, similar to the SQL's where clause, there's a where clause. And the main difference is in this match clause. Match is where you perform joins between your account or node records using the relationships between the nodes. Instead of kind of specifying a set of tables there, you do specify these graph patterns. Okay, but they're SQL-like, they're meant to be SQL-like, and the outputs of queries are tables. So this query is asking for all transfers that have originated from Alice's account and then does a group by and aggregation by the owners of those accounts and takes the average of, essentially asking how much has Alice sent to each account owner on average, right? But the outputs are tables, okay? So the main part is that there is this different way of specifying your joins, and in particular, you do adopt this path syntax. And this has several usability advantages. So the most obvious advantage that people kind of like about graph database management systems, that it makes asking recursive queries much, much simpler compared to SQL. Right? So if you had a question, for example, give me all direct or indirect e-transfer money flows into Alice's account from Canada, so the question is asking not only the direct transfers between into Alice's account from Canada, but also 2-hop or 3-hop or even longer ones. There's a very elegant way to ask this in Cypher, for example. So you just put the clean star into the e-transfer relationship in your pattern, in your join. It's basically similar to the string regular expressions, kind of inspired by that. So it's asking for essentially all possible sequences of e-transfer edges. And the outputs of these would be actually paths. So paths are actually native data types. So you can bound it to variables. You can return them as query results. And in this case, you're going to get a table of paths. For other classes of recursive joins, for example, if you were interested not only all paths, but shortest path, there's also specialized syntax in the query languages of these systems, which again make it a lot easier. If you ever had to written recursive queries in SQL, you know how painful it is. In SQL, recursion is an afterthought. It came into SQL 20 years after SQL was originally designed, and it's kind of a mess. So people, it's really one of the Achilles heel of SQL is recursion, and these query systems, graph databases, make it a lot easier to ask these recursive queries. A second usability advantage is that it allows users to essentially ask these flexible join sequences. So if you ask, for example, give me all flows of money into Alice's account from Canada, so now you're no longer interested in sequences of e-transfer edges, but you're interested in all combinations of essentially paths that might flow into Alice's account. So maybe e-transfers followed by wire, or EFTs followed by wire, followed by e-transfer, so on and so forth. There's again a very nice way to ask this in a query language like Cypher, where you just omit in this relationship pattern between the two accounts the type of the edge, which essentially instructs the system to take all combinations of joins that you can do across these sets of records, and will do it automatically for you. You know, to do something equivalent in SQL, you'd have to specify for each, and in this case, the query is recursive, for each possible depth of your recursion, for each possible types of joins that you'd have to do, which would be very painful. Okay, and you could also do similar to string regexes, put patterns on the types of kind of paths that you want to match, which again gives you this flexibility of taking unions of joins with this nice elegant syntax. And the last part, the usability feature, and this motivates a lot of the applications that are built on these systems, is that it makes it, you know, arguably simpler to ask for when you're searching for patterns across your record. So for example, if you were building a fraud detection algorithm, a fraud detection application, and you were interested in patterns where maybe there is a source account that blew icon that I'm showing that is sending some amounts, maybe small amounts, but spreading it across to multiple accounts. And then all of them are being funneled back into this common account with some pattern. Maybe the middle nodes are getting a bit of cut, so the second kind of transfers are a little less than the first transfers. You think of this when you are building the application as a pattern across objects, across entities in your mental model. So those are essentially the query languages of graph databases. Because the joins are expressed as patterns, are easier to compose. So you are in a more direct relationship to the pattern in your mind. So in this case, this would be the query asking for that pattern. And as you can see, really you just draw each kind of path that you had in your pattern into the query language. And this is kind of the core motivation, is that a lot of the applications that are being built on these systems are looking for patterns across the sets of records that have been kept in the enterprise. So fraud detection, risk detection, recommendation engines are some of the core classes of applications that are motivating this class of systems, right? So I entered this area about 8 years ago, and when I was entering, there was a lot of suspicion about, not every class of database management systems that are being proposed every decade live. Some of them kind of are, they have their own decade, and then there's no real commercial activity. It doesn't pick up. There's no real adoption. But I think those questions are now settled. I think I would argue that I'm convinced these class of systems are quite successful. They do see wide adoption. And some of the evidence for that is that we do see now some industry standards. ISO, for example, after SQL for the first time, standardized property graph query languages. GQL came out this year or last year, but it's the first ISO query language standard it's in SQL. And SQL also adopted a new property graph extension. So there is an official SQL extension where you can get the query languages that are similar to, or the clauses that are similar to what I showed in the previous slide. Okay? So in a nutshell, that is kind of the class of systems that we nowadays call graph database management systems. So Kùzu started as a project that aimed to essentially perfect the feature set that I mentioned. So be a state-of-the-art system that is very good at recursive queries or finding patterns. And I'll kind of tell you in the technical part of the talk kind of what is the main challenge when you're essentially searching for patterns across your graphs, data that you're modeling as graphs. And we focused on high scalability and very fast querying. So that my 10 years were essentially spent on trying to understand the principles of how would we develop a modern graph database engine, and what would its query processor look like, what would its storage look like, storage structures look like, so that we can kind of push the field in terms of scalability and performance, which were kind of the two main, I guess you could say two main features of any database management system or value adds of any database management system are these two, but especially in the market of graph database management systems, these were essentially big pain points when we talk to users. In terms of our usability, Kùzu is like SQL-like, or if you're familiar with a more modern system, DuckDB. So it's a library. It's not a server, so you can embed it into any of your applications. And it's open source, it's free, and it's now being, again, commercialized. So there's a more serious engineering team that is developing it. And the system is at a stage after 4 years where I can comfortably tell people you can start using it. It's mature enough. You can build applications on top of it. So if you do research that requires a kind of a database management system that has this querying capabilities that I mentioned, I think Kùzu is the system that you should use. All right. So let me now come to the technical part and tell you about this one system, one principle that I'll tell you that I think every graph database management system should integrate, although I wouldn't make the same argument for relational systems, which is this technique called factorization, right? So here's the core challenge when you're trying to build a competent graph database management system that aims to be good at finding patterns across records, right? So suppose I'm looking for this pattern. I've got this 3-hop path that I'm looking across my nodes, where the age of the first node is smaller than the age of the last node. And maybe I'm going to project out the IDs of the A node and the D nodes, okay? So the core challenge when you have essentially data that people model as a graph is that graphs have this core property that records connect to other records in a many-to-many way. So like one account, so think of the financial transaction network example that I gave. One account is going to transfer hundreds of transfers to other accounts, which will transfer hundreds of transactions to other accounts, so on and so forth. So the search space of the patterns that you look at grow exponentially by the average degree. So as a general rule, if the average degree is 1,000, each account makes 1,000 transactions. So for this pattern, it's a 3-hop path. There is 10 to the 3 many possible intermediate combinations that you have to first enumerate and check if the pattern, what is specified in the where conditions, essentially match, okay? So the key takeaway of the talk, and I'll be able to focus actually only on one of these, is that there has been very exciting theoretical work in the database theory community that has argued and that has shown essentially that for some queries, the search space can be compressed, highly compressed. Right, so the search space might be very large, but you can actually compress it. And then for some other queries, cyclic queries, which I won't have time to get into, the search space is actually much smaller. So if you use smart join algorithms, or smart, say, traversal algorithms, the search space is a lot smaller than what it looks like. So you can actually improve over the standard join algorithm or the standard systems by integrating some of these ideas that have been coming out of the theory community. Right? So I'll talk about the first one. The first one is the compression algorithm, that the search space can be highly compressed, and that's the technique of factorization. Right? So let me kind of walk you through the idea of factorization, and then how do we integrate that idea and make it practical and put it into an actual system. Right, so here is kind of a state-of-the-art processing paradigm or principle in modern relational database management systems, or modern take any class of database management systems, right? So it originated from columnar relational database management systems. So the most popular ones nowadays are like things like Snowflake or DuckDB. So they essentially are based on this paradigm called block-based or vector-based processing at a time, okay? So here's how this works. So suppose you had the SQL query, right? So select department average age from the employees table where age is greater than 30, and we're grouping by department. So the query is asking, on average, what is the age of my employees in each department, but only consider employees that are greater than, who have age greater than 30. So it's a very simple query, and take any system that you want, especially the columnar systems, who are the fastest kind of systems for these types of analytical group by and aggregation queries. There's only one plan that they will generate. The plan will look like essentially a scan operator that will scan all the tuples their age is greater than 30 from the employees table and pass those to a group by and aggregate operator, which will perform the group by and aggregation, right? So in block-based or tuple vector-based processing, in this paradigm, here's how processing happens. Each operator, so this is the core principle, each operator always operates on a vector of tuples, often about like 2048 tuples at a time. Right. So every operator in the system needs to be written so that the operator essentially has a tight for loop that loops over a vector or a block of tuples and performs the same computation over and over again. So the way this would work is that the scan, for example, would take a vector of tuples, right? So in this case, I'm just simulating that it takes all the tuples in the table. And then its job is to identify the tuples that have age greater than 30. So in a for loop, we'll do this and identify the tuples that have age 30, okay? And then this will be passed to the group by and aggregate operator, which will perform its group by and aggregate, right? So this is good. It's very well understood that this is kind of state-of-the-art. It gives you great CPU utilization. But it's not really optimized for the many-to-many joins that is the core of the computation that graph database management systems do when they search for patterns. So what would happen in a graph database management system if you adopt this vanilla vector-based processing is, suppose you're looking for this two-path query where it's asking for essentially all the, say, transfers that Liz's accounts might be facilitating. So where the middle node B has name Liz. Okay, and suppose this is my graph, and the nodes with label L are the ones that are owned by Liz, right? So scan is going to find all the accounts that are owned by Liz. And then these operators that I'm calling as extend are essentially join operators. They're going to extend the tuples that they get to either forward or backward directions to larger and larger paths. So by the time you essentially extended these Liz's accounts to your incoming neighbors and your outgoing neighbors, you're kind of destined to end with a table that looks like this, with an intermediate result that looks like this, where there's tons of repetitions. There's going to be L1, for example, that's repeated many, many times, and Liz is repeated many, many times, so on and so forth. And the reason this happens is that because in the nature of the data, it's kind of fundamental that each Liz account has 100 incoming neighbors and 100 outgoing neighbors. So you're going to produce 10,000 tuples, and the Liz value will be repeated in the intermediate results. All right? So this repetition happens because there's one group of vectors, and they're represented in this flat format. So factorization was this idea that you can essentially take relations, these intermediate relations, and actually, instead of adopting a flat representation, represent them as unions of Cartesian products. Right? So the main principles that this literature in theory was arguing was that as a system, you can just by looking at the query, without looking at the data at the compile time, figure out that there is some compression that you can do on these intermediate results without ever looking at the kind of the constraints you have at the storage layer. So, I'm not going to go into the principles, but I hope it's very clear from the query that I had that if you fix the B node, for example, if the B nodes are fixed, that the incoming and outgoing of those nodes are conditionally independent. So you can actually get this much more compressed representation that's on the right side. So that's essentially the fundamental principle of factorization, is to look at a query, and by looking at the query, understand the conditional independences between the variables in the query, and then apply some level of compression. So I'll show you, in kind of wrapping this up, a very simple approach where you can take a vector-based processor and essentially extend that query processor to implement factorization so that your intermediate results are compressed on the fly as you're doing query processing, right? So here's the general approach that we call factorized vectors. So I'll take exactly the same plan. The only change I'm going to do to the query processor of the system is that I'm going to change the way we represent intermediate results. So scan as before is going to scan all the tuples, and in a tight for loop will run its filter. And then the join operators, in this case extend A, what it will do is the first extend A operator, it takes a vector of tuples, okay, ideally 2048 tuples, and then it will, the first thing that it will do is that it will flatten the tuples that it took. And what that means is that I have this additional current index field over there, which is -1. The meaning of that is that -1 means that all of those tuples are live during the computation right now, right? And extend is going to flatten it by setting it to a single value. Okay, so now it's going to say that instead of however many tuples you had, only one of them is live. And then write the results of the join, in this case the incoming neighbors, to a separate vector. So I'm no longer passing a single vector that has all the results in a flat manner. I am passing two vectors right now. One, the factorized vector 1 group, and the second group to extend C. So that operator takes essentially two sets of vectors that are factorized. And then what that will do, what C will do, is that it will write the outgoing edges into a separate value vector. Okay? So basically the meaning of this, the intermediate data that is being passed between these operators is that we are passing essentially 10,000 tuples right now. The Liz one, Cartesian product with the 100 values, that's been written to a separate set of vectors, Cartesian product with another 100, and that's being passed to whatever is the next operator, say in this case maybe a result writer or a sync operator. Okay, so during the pipelining, the query goes back and extends the current index to 2, writes a new set of 100 values to output the other 10,000 outputs in this case to the next vector. Okay, so here's just a very simple micro benchmark on the fastest system that I know in the world. It's called Umbra. It's from Technical University of Munich. It is the state of the art when we do performance comparisons in the database system. Just to pinpoint that just this intermediate growth is not handled in these state of the art systems, let alone in the highly adopted systems like Postgres or Snowflake, any of that. So you do need to integrate these ideas about compressing these search spaces if you want to be popular. So you do see it's a very simple 2-hop query from a TPCH kind of benchmark in the graph databases. We do see 1 to 2 orders of magnitude query performance differences if you adopt these idea of factorization. All right, so I'll stop there. I think I'm running out of time. There's one more thing that I want to say, but what I want to say is, so Kùzu has been in development for 4 years now. There's a professional, essentially serious development happening on it. And the system is at a state where I'm now comfortable telling my colleagues and obviously anybody who is building applications that it is mature enough that you can build applications on top of it. And here's the tons of papers we had written as part of Kùzu and the prior research that we did. All these on the principles of factorization, as well as these other types of modern join algorithms that needs to be integrated into these classes of systems. So I'll stop there and take questions. Thank you.
Getting back a little bit to Eric's talk and things that come up. Do any of when you're implementing a query, you have choices of ways to do it. Do your techniques or closely related ones, any of them deal with probabilistic methods by doing some sort of sampling? I realize that you can sample and things will look good and then you get along somewhere and things blow up. But is there any serious work of that nature?
No, not in any class of database management systems that I know. So during query processing, the only place where sampling happens is the queries. When you're generating plans for the queries, you're generating this relational algebra trees, essentially. And there you have tons of choices. There's tons of equivalent trees that will correctly evaluate the same query. The only place where sampling happens in some systems, and it's now very popular, is when you try to kind of understand trees that will generate smaller intermediate results. So you do sample from the base tables to see what would happen, for example, to these intermediate operators in these plans to be able to pick better plans. So it only happens during query optimization, none during query processing. There's a class of systems, and there's some startups around us that do approximate query processing. So database systems that aim to tell you very quickly, probabilistically, the outputs of aggregations, for example. So you don't have to go sort of scan terabytes of data. They use sampling on base records during query processing. But none of the systems that are really in the classic classes of systems that are in practice.
So there's definitely the issue that something that looks good by some experimental techniques blows up somewhere where you haven't pushed.
Yeah, of course.
And
yeah,
that's
of course.
probably a reason that they're not as pushed.
There is a query for every system I can think of, tons of queries where I can make them blow up very, very easily. Every system, any system, Postgres, Umbra, doesn't matter, bring it. There's very easy to write queries that will blow them up, yeah.
Great work. So actually, the question that comes to mind is about query planning as well. I think after all this factorization, eventually you need to flatten it up and maybe do some selection or scan on the flatter results. Do you ever need to do it midway in the plan and then like flatten it, do something, and then factorize it again? And how do you incorporate that in the query plan?
Yeah, that's exactly how it happens. So we kind of do it. So the work that I showed kind of was on how would you integrate it into the query processor, but it doesn't answer the question of how should you come up with plans that are good once you're evaluating factorized intermediate relations. So the question of how do we generate good plans that generate factorized relations isn't that well understood. So it's more, we do this more in in a kind of a greedy way. We start with a plan, and whenever we can factorize, we factorize, and whenever we have to flatten, we flatten. So that's the approach that we took because of simplicity and kind of lack of understanding of how do we generate kind of good plans that are factorized. You can show that, theoretically, factorization gives you polynomial size reductions in the intermediate results that you generate on whole classes of kind of queries. But you can show that it's generally like NP hard, all those results to pick the best one in the worst case at least, so on and so forth. So there's some reasons to believe that, optimization in databases is always a hack, basically. It's always a heuristic. So you do only implement in your system the very simple versions of these techniques. So that's because of the nature of the complexity of the system.
So I guess when you started off with your entity relationship slide and graphs and so on, I was on board and I thought, well, what you're going to talk about is Alice has some connection to Bob, and then suddenly I feel like you threw a curveball and said, now we're talking about transactions between Alice and Bob, and that's not exactly what people normally represent in a graph. And so I guess what I'm puzzled by is sort of putting that together, that nobody wakes up in the morning and says, well, I wonder if Alice is a terrorist. They want a standing query for that, and you're logging transactions, and the graph is about maintaining relationships that are more static. So isn't the question I have, getting to that, is well, how would it change if you said, what I want to do is have standing queries so that I'm processing a log of transactions? And
so you mean as if the data was streaming?
yeah.
So first of all, it's not true that people don't do fraud detection applications kind of after the fact. Most of the fraud detection application builders that I've talked to also complain about this, because banks actually do analyze after the fact. A lot of the fraud detection applications running in the banks actually, they are not able to catch the fraud as it's happening. It's always, there's an analyst sitting somewhere and there's a report that will essentially use some tools to actually analyze to see if this set of transactions that happened are suspicious. So, this sort of after-the-fact analysis is actually very common. People obviously do want to get to the fact that can we catch it as sort of a stream of transactions are coming. So you're getting into this essentially this continuous query processing, continuous sort of how do we catch this on the fly. And I did some work in that space, but in general, yeah, so there isn't anything practical that I think, any system that's practical that is excelled at that. I think that is an area that's just very difficult in general, to build very practical systems that will catch things on the fly, simply because, the data, if you're getting continuous stream of data, you can only keep a window of it. And within the window, people do stuff. But to try to find frauds that have taken maybe 6 months to actually perform, like maybe some money transfers that have taken 6 months to perform. People aren't able to catch that, generally. Yeah. All right, good. Thank you very much.